everyone. Welcome to the sixth episode of the Scientific Saturday lecture series. These lectures are our endeavor to take global science to the students residing even in the remotest corner of the nation. Myself, Vishaka, founder of Gurukul Academy. Our guest today is Professor Daniel Angerhausen. He is an astrophysicist and astrobiologist at the Institute for Particle Physics and Astrophysics at ETH Zurich, where he leads the project office and the science team lead for the Life Space mission. He's also the founder and CEO of the science and tech communication startup, the Explainables. On his search for planets around other stars, he has flown 5 missions of NASA Airborne Telescope, SOFIA. He's also a mentor and science committee member of NASA Frontier Development Lab. This is an artificial intelligence machine learning incubator tackling challenges in various fields of space sciences in collaboration with industry stakeholders such as Google Cloud, NVIDIA, and IBM.
Hello, I'm Rishabh Nakra, founder and admin of the Secrets of the Universe. Before we invite Professor Daniel Engerhausen for his lecture, I would like to remind everyone that we'll be taking questions after the presentation. So all of you can post your queries in the comment section and we will be taking it once the lecture is over. We welcome you, sir. We are very fortunate and privileged to have you with us today. Without further ado, we request Professor Angerhausen to begin the session.
Welcome, sir. Thank you
Hello,
so much.
everyone. Yes, thanks for the
Good evening,
introduction. Thank you. Good to be here. Yes, great. So there are my slides. Yeah, also hello to everyone from my side to my seminar today about aliens, exoplanets, and astrobiology. A short introduction to how we are currently searching for life in space and mostly life in space outside of our solar system. And first, I want to start with a quick introduction of myself. You already got a lot of the information. So I'm currently a senior scientist at ETH in Zurich. I'm also part of the team and one of the founders of Explainable Science Communications, where we help other academics to communicate their science better, not just with the public, but also within their communities, with policymakers, other stakeholders. As was already mentioned, I also was part of the NASA Frontier Development Lab, where we worked, for example, together with Google Cloud and NASA on solving some of the big challenges in space sciences with machine learning and artificial intelligence. By the way, this guy here in the image, this other one is a Neanderthalian, and I'm actually from Germany, pretty close to where Neanderthal actually is, so that might explain this similarity here. So my background, I'm born in Germany, I've lived in the US for quite a while, and now I'm in Switzerland, in Zurich, and working there. Just a quick summary of where I went in my scientific career. Okay, so let's start with this term of astrobiology. So maybe not all of you are familiar with it. And what is astrobiology? What does this mean? It's a relatively new field of science. And when I try to explain it, I always start with this old legend. It might actually be an Indian legend, but somewhere from South Asia, if I'm not mistaken, the legend of the blind man who found an elephant. So the story goes that a group of blind, wise men find an elephant and can't really figure out what it is. So one of the wise men is at the back, feeling the tail of the elephant. It's like, well, this feels like a rope with a brush at the end. The second one is touching a leg and says, like, I'm not sure. For me, it's more like the trunk of a tree. The third one is touching the teeth and it's like, for me, it feels like the tip of a spear or something like that. So each of these blind men has a very different perspective of this elephant. And only if they take all the information together, they get the full picture of what this elephant is. And this is really one of the core problems or one of the core challenges within astrobiology. So we can't understand life in space on our own as astrophysicists or as biologists. We really need input from a very large number of different fields like geology, chemistry, sometimes even social sciences, to understand this phenomenon of life in space. So it's really by definition, by design, multidisciplinary approach to study life in space in this field called astrobiology. And since you all were talking about, or maybe a lot of you, entered the entered this talk to hear about the aliens, I actually will start with these aliens and talk about a couple of aliens, and actually aliens that live on Earth. And we call them extremophiles, and in a second I will explain you why we call them. And here's our first example, the blobfish, back-to-back ugliest animal in the world, 2015, 2016, which is actually not really nice because this blobfish doesn't look that weird in his natural habitat, which is very deep down in the oceans at super high pressures. This is really only how the blobfish looks like if you take him out of that environment into normal pressure that we are here at. And that thing that makes this blobfish an extremophile, so a organism that loves the extreme, is that it lives in this very high pressure environments, very deep down in the ocean. Another example for an extreme loving animal is the ice fish. So the ice fish lives in the Arctic regions, basically at the freezing temperature of water, very close to the freezing temperature of water, and it really thrives in these environments. And on the other hand of this temperature scale, there's the Pompeii worm. That's a worm that lives at underwater volcanoes, so basically at the boiling point of water. So around 100 degrees Celsius is where this Pompeii worm thrives and reproduces and really lives. So this is what we call in astrobiology extremophiles. Animals, organisms, microbes that live under very extreme conditions. And they are so interesting for us in astrobiology because these conditions might also be the conditions in space, in environments on other planets where we would search for life. So the blobfish, something like the blobfish could, for example, live very deep down in the oceans of Europa or some of the icy moons. There might be, some volcanic worlds with underwater volcanoes where something like the Pompeii worm under very hot temperatures could survive. So just learning about these animals that withstand extreme conditions on Earth, we also could learn how they survive or even thrive or even originate in these extreme environments on other planets, for example. And I brought another one that actually even looks like an alien a bit, or at least like an alien from the movie. The Latin name is Tanea solium. And I only give you the hint, so it's a homework for you to look up what that actually is. As a small hint, it actually lives inside of humans, and statistically, I'm not sure many people are watching here, but there's probably, depending on how many people are currently watching the stream, there might be 10 to 50 people in the audience who might actually have one of those inside of them. So just a little homework for you to figure out what that one is. So this is extremophiles, right? So animals who love the extremes, and my favorite of these extremophiles is the tardigrade. So maybe some of you have heard about this little guy here. Looks a little bit like a gummy bear floating here in water. And this is really, if you could design a miniature astronaut, you probably wouldn't make it much different than the tardigrade. So this tardigrade can put itself, if you deprive it from water, it can put itself into this here in the bottom picture and kind of like a cyst state, almost like a turtle. It puts itself in this shell, and once it's in this state within is turtle shell within its spacesuit, so to say, it can withstand gamma radiation. You can deprive it of oxygen. You can put it in liquid helium, and it would survive for more than 10 years sometimes. And then after 10 years, you just put water on it, and it starts to survive, or it starts to live again. So really, this is an amazing adaptation of nature for these super extreme environments and super extreme conditions. So this is actually what makes a tardigrade a much better suited astronaut than humans, for example. I mean, we are really, we wouldn't withstand any of these conditions out there, whereas a tardigrade is much better suited for this. So again, one of these extremophiles that are a huge area of study in this big field of astrobiology. Maybe some of you know this quote from a very famous book, The Hitchhiker's Guide to the Galaxy. And the point I wanted to make here is that often when people hear about me, I'm an astrophysicist, I work for NASA, people are like, oh yeah, I'm pretty sure you talk to aliens all the time, admit it, there's a secret bunker where you talk to them. And then I usually ask people, so why would you even think that if we find aliens, that we could communicate with them, right? I mean, we are not even able to communicate with the next smartest species on our planet, let's say dolphins or chimpanzees. They have the same DNA, 99% the same DNA as we, they breathe the same air, drink the same water, and yet we cannot really communicate with them, right? I mean, some people think they can talk to their cats or dogs, but didn't we even establish a communication with other species, intelligent species on this planet? So why are we even so arrogant to think that we could immediately communicate with aliens, right? And this is actually also one tiny part of this big research of astrobiology. There indeed people, for example, here at the SETI Institute, that searched about, that thought about the question to study animal communication, to eventually also learn about how we could, under certain circumstances, also talk to aliens, right? So really, the study of animal communication is also part of this huge field of astrobiology. So you can see it's not just geologists, chemists, it's even linguists. Sometimes it's even social scientists who think about the social impact. What would it mean for societies if we find life in space? So really, it's a really, really multidisciplinary field. And if you are not necessarily in astrophysics or biology, but interested in this field, there might be also ways for you to contribute if you're in social sciences, if you are more in the so-called soft sciences. So there's really, it's really a multidisciplinary effort. So the question is, so what am I working on, right? So I'm an astrophysicist. What is my piece of this puzzle? What is my contribution to this field? And if you ask me, at a party what I'm doing, I'm usually saying, yeah, I'm an astronomer and I like to climb high. And I don't just mean here in Switzerland, climbing up to the mountains. I mean, as astronomers, we really like to put our telescopes as high up as we can. So here you can see a younger version of me at the beginning of my PhD studies at some of the best telescopes in Hawaii and Chile, which are really some of the best places in the world. They are usually pretty high up, pretty dry, where we put our telescopes. So this is one way to put the telescopes as high up as possible. But then if we want to get them even higher than the mountains, we also put telescopes in space. So one example I brought here is the Cheops telescope, a telescope dedicated to characterizing extrasolar planets, which was actually built at Bern University, where I was working for a couple of years until 2 years ago. And then the James Webb Space Telescope, which probably many of you have heard of, was just launched a couple of weeks ago over Christmas. And so this is if you want to get even higher than the mountains. And also here, I brought a quick example to get an idea about the size. So get a picture of me and the telescope. So this tiny 30 centimeter mirror here in the back, that is a Cheops telescope. You can see us here in these bunny suits, how they're called, in these masks and full cover suits, not because it was during pandemic times. It was because this picture was actually taken in a clean room. So these telescopes are built under super clean conditions. You can imagine you don't want, a hair from a mustache fall off and then stick to the mirror. And then every time you look at a star, you just see my mustache hair. So really, this is why these telescopes are usually assembled in these clean rooms under super clean conditions. And that is why we are wearing these suits here. And then also here on that side, that is the actual James Webb Space Telescope in the back of the picture. So this again is also a clean room. So behind this window here is one of the largest clean rooms in the world at NASA Goddard Space Flight Center, where I used to work at that time. And you can see this is a ginormous telescope. So whereas Cheops was, this relatively small 30 centimeter telescope, this James Webb Space Telescope is a 6.5 meter gold-coated beryllium, set of mirrors put together. So this would even be a huge telescope on Earth, and it's really like an amazingly big, space telescope for its purpose. And it's actually so big, and some of you might have seen these videos already during the launch of James Webb. It's so big that it doesn't really fit unfolded in the top of a rocket. So you might have seen the Ariane 5 launch. So the fairing, the top tip of the rocket wouldn't fit the telescope when it's completely unfolded. So it really had to be folded together, tightly packed to fit in this fairing. And then over the past 6 weeks or so, it unfolded itself. You see here these solar sails oh, the solar protection cells are going out. Then soon you will see how the secondary mirror folds out, and then how the other mirrors fold out. So it's a bit like a transformer, this transformer toys for kids or something like that. So it's so huge that you can't shoot it into space completely unfold. And you can imagine for all these people that want to use James Webb, and all the people who build, all the engineers who built James Webb, that was really a nervous time for the last 4 to 6 weeks, when all these, I think about 1,000 mechanical processes happened to unfold this telescope. So a lot of us were just reading through the NASA blog. Okay, today the mirror unfolded, today this worked, and everything worked. And it's really, everyone is really happy in the community that all of these things worked out. So really amazing technology, super congratulations to all the engineers involved, that everything super worked out in space. So this is really amazing work, and now every one of us is waiting for and looking forward to using it for astronomical observations. So then the question is, why are we getting high with our telescopes? Why do we put them on the top of mountains? Why do we put our telescopes in space? And one might think, yeah, you're closer to the stars, right? So that may be an intuitive answer, but that doesn't really make a difference, to be honest, right? If something is, a trillion light years away, why would going a couple hundred or maybe a kilometer or two closer really make a difference? The real reason is this blue region that you see here. So this very thin layer of atmosphere on top of our planet. Because you can imagine, if a light particle, a photon, comes from somewhere in space, it's basically flying through a vacuum for most of the time. So there's nothing really between the light and between the star, let's say, where the light is coming from, and us. But then on the very last part of its journey, the light particle goes in our atmosphere, and then there's air molecules. There's all sorts of things that might be absorbed, it might be reflected, it might be scattered. So there's so many things that could happen to this light photon just on this tiny little last part of its journey to our telescopes, that we want to avoid as much as possible the Earth's atmosphere. This is why we put our telescopes as high as possible. And it's actually even worse for certain other parts of the light. So some of you, for example, might have heard about the ozone layer, that it's absorbing the UV radiation, right? So there's layers in the atmosphere that absorb certain kinds of light. So the ultraviolet light you can see here is absorbed very high up in the atmosphere. That, on the other hand, means if I am a UV astronomer, if I'm interested in ultraviolet light of stars, planets, I can't observe it from the ground. So I really have to put a telescope in space to observe ultraviolet light. And it's the same for gamma rays, X-rays. For most of the microwave, you have to go to space. It's really just the visible light that we can observe from the ground, and the radio emission. And this is also and therefore it's also no coincidence that our eyes work in the visible light, and that radio works, our phones and radio, the TV works in radio frequencies, because that's the only radiation, the only electromagnetic waves that go through air. Everything else is absorbed in our atmosphere. So this is really why we need to put these telescopes above the atmosphere to even catch that light. So then you can see here in the infrared light, so really slightly next to the red light that we can still see with our eyes, is this infrared light that some animals are also able to see. So this is so the infrared light, which is also very interesting in terms of things we could learn from infrared light in various clouds in space, on planets and stuff like this. That infrared light goes in our atmosphere and is absorbed about at the altitude where planes fly, right? So about 10 to 12 kilometers up in the air, a lot of this infrared radiation is absorbed. So that also means if I'm an infrared astronomer, I can't really observe a lot from the ground. So I also have to get higher up to get this infrared light, collect this infrared light. So then you might think, okay, so in this scheme that he's showing here, this plane is just shown here so that you get a roughly idea how deep the light goes into the atmosphere, right? No one would be so crazy and put a telescope on a plane, right? Well, wrong. There's actually such a thing like a telescope on a plane. It's called SOFIA, the Stratospheric Observatory for Infrared Astronomy. It's a joint venture, a collaboration between the German Space Agency and NASA. And as you can see here, it's basically a Boeing 747, so jumbo jet with this garage door on the back. And then behind this garage door, there's a telescope installed, and you can observe from up there in the stratosphere. And when I was a student at Cologne University, which was, building parts for the instrument, 10, 15 years ago when I started my career, one of my biggest dreams was to maybe, build one of these instruments, or maybe put a screw on one of these, boxes that get installed on Sophia. And today I stand here and can say that not just, my screw or my instrument flew on Sophia, but that I myself flew on Sophia a couple of times. You can see us during the passage to our observation, flying over the Grand Canyon. Looks a bit like Mars. Yeah, and this is really how it looks inside of the plane. So very different from, what you might be used to from commercial planes. And so really nice compromise between observing from the ground, because it's a telescope that can come home every morning. Every morning can put a new instrument on it. It's not like a satellite that you once put in space and then you can't maintain it. You can't fix it if you have a problem. So really putting this telescope on a plane is a nice mix of having a telescope on the ground, but at the same in kind of like space-like environment up there. So this is why Sophia is a really unique contribution to observing that special light in the infrared. Yeah, and again, here, picture of me to scale so that you get roughly an idea that it's actually the size of a plane. For those of you who still don't think that Sophia is a really cool thing, also two more pictures. So one is Sophia as a playing card. So for those of you who like, card collection and these trump games, Sophia has a card in one of these games. And then the ultimate geek credibility test, I guess, is that Sophia even had a cameo appearance in the Big Bang Theory. So I think it's Sheldon's lab or Sheldon's home. I'm not sure. He has this tiny model of Sophia in the back of the Big Bang Show, and I actually have the same one on my desk at home. So I think after this, really, everyone should love Sophia, right? Okay. So then the question is what I personally am observing with it, and what my work is on is what I call alien worlds. Sometime are exoplanets, extrasolar planets, planets around other stars than our sun. And as of today, we know more than 4,000. So this number here is from, I have to update my slides, I guess. So I think we are at 4 or maybe even almost at 5,000 planets around other stars that we've already found since the first detection of one in 1995. And actually, this observation was made in 1995 by two of my colleagues from Switzerland. So Didier Queloz here and Michel Mayor. He actually has, Didier has the office 2 down from me at ETH in Zurich. And they got the Nobel Prize in Physics 2 years ago, or almost 3 years ago now, for the detection of the first exoplanet in 1995. So really a revolutionary observation that really started this field and also started or kick-started people thinking about astrobiology again, right? Because once we found the first exoplanet and then started to find more and more of them, it became also more and more important to think about, okay, are there Earth-like planets? And if so, do they have life? So really this opened up this whole area of research. So then you might think, okay, so if this is, something that was found 25 years ago and you found 4,000 or 5,000 by now, it seems to be relatively easy, right? Well, it's actually super, super, super hard to find these extrasolar planets. And to illustrate that, I brought this video. This is actually real data from a NASA solar telescope. So this is a telescope in space looking at the sun 24/7, basically. And then you can see here this tiny little black dot that is going over the screen, right? So this is the planet Mercury while it is transiting between us and the sun. So every couple of years, I think, we have the planet Mercury going between us and the sun. And this gives you an idea how hard that is for us astronomers to find planets around other stars, right? I mean, admittedly, this is still like the smallest thing that we still call a planet. And these images are also taken in colors where the sun is relatively active. So it also looks like the sun is, really, really exploding in some parts at some point. But this gives you an idea what challenge we are facing when we want to find them. So we want to find these tiny little black dots in front of these giant balls of fire that are exploding. You can see here in some colors, these explosions are even brighter or bigger than these planets in front of it, right? So this shows you how hard it is for us to find planets around other stars. But this video about Mercury transiting the sun not only shows the challenge, it actually also shows one way that we use to find these exoplanets. Because sometimes we are not so lucky, not just lucky that we see a transit of Mercury in our solar system. Sometimes if the orbits are aligned in the right way, we can also see planets transiting other stars out there. So some of you might have heard about the Kepler Space Telescope, for example, or the TESS Space Telescope. They use this method to find planets. So they look at stars, and then some of these stars have these dips in their brightness. So almost exactly after the same time, again and again and again, their brightness goes down, almost like a heartbeat, right? Every 3 days, every 14 days, every 60 days, the light of the star goes down a little bit. And this is when a planet moves between us and the star. And by measuring these reoccurring dips in brightness, this heartbeat of the stars, we can conclude there must be a planet going between us and the star, and again and again. And then from these light curves, we can find out the size. Bigger planet makes a bigger dip in the light curve. A smaller planet makes a smaller dip. Depending on how often these dips happen, we can of course also then say what is the orbital period. So from these observations, we can learn a lot about these planets too, even though we're not directly observing them, right? So this is not just showing the challenge, but also one of the ways to observe them. And there are different methods, but for now I'm just focusing on this transit method. There's another method called radial velocity. There's a method that uses microlensing, direct imaging. There's also a way, if you really suppress the star, the light of the star, to separate the planet. So there are various methods, and this is one of the methods how we find and characterize these exoplanets. And that's also the kind of observation that I did with Sophia about 7-8 years ago. I worked on this topic during my PhD thesis, so I theoretically showed that it should be possible to do these kind of transit observations with Sophia, and then it took a while to convince people of it, wrote a proposal, and then eventually I got my chance to prove it and to get this time on Sophia to do this observation. Here you can see me and the team at this night on October 1st, 2013. So here you can see me in the corner, the only one who's kind of like happy that it worked. The rest of the team seemed to be just, a bit annoyed that they had to work for me, I guess. Also for the girls and women in the audience, on this particular flight, the mission director, one or two of the instrument scientists, and a couple of the telescope operators were women. So don't let anyone tell you that at NASA you can't work as a woman, or this is just work for the guys. So this mission, this flight, this observation wouldn't have happened if a lot of really amazing women were involved. So to the girls out there, there's space in space and at NASA for all of us, not just for the guys, right? And long story short, so what we observed that night was this kind of data. So you can see here, we observed the brightness of the star, and then the brightness of the star went down for a couple of percent, which means it's a pretty big planet, kind of like the size of a Jupiter. So about 1-2%, the light went down. And then after a while, the light of the star came back to full phase here. And this was the first observation of such a transit from a plane, and this day with Sophia. This was me on the next morning on the way back. So really happy that our observation went well and that everything was cool. So again, I could be sitting in the cockpit for a touchdown. So that was a really amazing experience also for me to do this observation and fly on this plane. And as I mentioned, this planet we observed at that time was a really big one and really close into a star. So it's really a planet that we don't have any analog in our solar system for. And this is one of the examples of these crazy alien worlds, planets that are really, really different from the planets in our solar system that we find out here. And this is an example for the class of so-called hot Jupiters. So planets the size of Jupiter, very, very close into their stars. Some of them so close in that they really blow off their atmospheres. Others so close that they lose some mass to their planets. Some of them are always facing the same side to their star, so that one side is really, really hot. The other side is a little bit colder, but still, super, super much hotter than the planets in our star. So really a kind of planet that was completely new to us when we found them. Another really strange and new kind of planet that we found are planets in this intermediate size. So once we started finding these thousands of planets with Kepler, with TESS, with other ground-based surveys, we figured that actually the most common planets in, at least our neighborhood and probably also in the universe are in this intermediate size between Earth and Neptune. And this is really a size where we don't have an analog in our solar system. So we got all these rocky planets, Earth, Venus, Mars. And then we got these gas and ice giants, starting with Neptune and then Saturn, Jupiter, etc. But we don't have anything in this intermediate size. And for a long time, people thought, yeah, this is just, you can get either or from planet formation. You either get a small one or a big one. But what we then realized is there's a huge class of planets of intermediate size. And one of the questions that we actually already able to answer today is to figure out, are these, which of those are just blown up big Earth, or which of them are just, small ice or gas giants, so-called mini Neptune. So this is really where we are at now. So this somewhat smaller planets that we can slowly but surely start to characterize and figure out, is there a transition region? What are the size of super Earths? What are these mini Neptunes? And then, of course, so to say, the holy grail of this whole exercise and, the key question of astrobiology, at least of astrobiology outside of our solar system, is to find so-called biosignatures. So in the spectrum, in this, in the light of the planet, to find certain signatures of molecules, of chemistry in the atmosphere that can tell us that there must be life on this planet. And one example for what could be one of these biosignatures under, certain circumstances, of course, has to be the right temperature, the right size of the planets in the first place. And there's other things like the star shouldn't be too bright, but also not too much UV. So there's a lot of context information too. But simplified, if we find oxygen and methane at the same time in a planet, that might be a pretty good sign, a pretty promising sign that there could be life on the planet. And the comparison or the explanation, the analogy for it is, it's a bit like grad students and pizza. If I buy a couple of pizzas, put them in one room with a bunch of grad students, what happens? Well, after 10, 15 minutes, all the pizza is gone usually, right? So that means if I find grad students and pizza at the same time, someone has just delivered the pizza, right? If it wasn't just delivered within the last 10 minutes, the grad students would have eaten the pizza, right? And it's kind of like the same with oxygen and methane. If I find both at the same time in an atmosphere, typically they would destroy each other chemically. So either the oxygen would eat the methane or the methane would eat the oxygen. But if I find both at the same time, it means I need a process that produces both constantly. And this is how we can conclude there must be life, if both of them are present at the same time. And more generalized, what we look for in biosignatures is something that is somewhat out of the equilibrium. So if it was just, physics and chemistry happening, everything would be in some sort of equilibrium, just, nothing going on. But if some things are, taken out of equilibrium, that might be also a hint that there could be life, something strange at least happening in terms of, planetary chemistry and things like that. So that's just as an example how we get to these things that we call biosignatures. And of course, this is a really tricky topic, right? So planetary atmosphere is not just, the life and the air. There's a lot of other things going on. So there's volcanoes that that might be putting methane into the atmosphere. There's interactions between the ice and the atmosphere. There's some interactions happening in the upper atmospheres. There's lightning. There's exchange between the oceans and the forests. So there's a lot of different things going on that really make up the chemistry and the molecules inside of such an atmosphere, right? And this is a typical example where we need where we need this input from different fields. So this is a typical example for this elephant problem that I described in the beginning. Planetary atmosphere is like this elephant, right? If I only understand volcanoes, I don't understand the whole thing. If I only understand ice, or if I only understand lightning, I don't understand this whole atmosphere thing. But if I put together people from atmospheric chemistry, volcanologists, glaciologists, and talk together in this big field of astrobiology, then we have a chance to understand this complex system of habitable, potentially inhabited planets. So where are we at now? So slowly but surely coming to a conclusion with this talk. So what is the coolest thing from my point of view that we already found out with our research right now? So we haven't found any life or any signs for it yet. But what I think is one of the coolest things that we so far already figured out with the Kepler Space Telescope, some of the other observations, is that depending on, it's still a rough number, but between, let's say, 5 to 20% of planets of stars in our neighborhood do have planets somehow similar to Earth. So it's same temperature, same size, that makes them eventually what we call habitable, so suited for life. So next time, if you go to the mountains, look at the stars, start to count, count every 5th, every 10th, maybe every 20th star that you count in the sky. There might be a planet that has the right conditions for life to emerge, for life to survive on there. So it's really a lot of potentially habitable planets out there. And with the next generation of telescopes, something that we are building or designing and working on at my university at ETH in Zurich, with a huge initiative all over the world, is the so-called LIFE telescope, which is really designed. It's actually an array of telescopes. You can see here, it's in the moment we are designing with 4 telescopes who combine their light in a central telescope. And then by combining this, we can really isolate the light of the planets from the light of their stars, and then can really go for planets the size of Earth and see if there's, for example, oxygen and methane in the atmospheres. But this is, maybe happening in 10 or 20 years. That's why we are pushing. But with something like this, the James Webb Space Telescope, we can get a first glimpse. We might be lucky and find a couple of these planets around somewhat smaller stars and can already start to look for water there, maybe for oxygen. But then with the next generation of telescopes, these LIFE telescope, for example, and other concepts, we really should be able to start what we call comparative planetology. So not just these 9 planets in our solar system and Pluto, but we should be able to look at other solar systems and should be able to tell if, these every 20th, every 10th star have a planet that is somehow like Earth, if these planets that are Earth-like are more like Venus, very hot and hellish planets, or cold and dry planets like Mars, or if these planets are really like Earth, this planet full of water that is really thriving with life. So this should be possible for at least 20 to 50 planets of the size of Earth in our neighborhood that we should get with a telescope like this LIFE telescope that we are designing and working on at the moment. And with that being said, I think we are the first generation in history that really has the opportunity and the right technology and the knowledge to systematically look for life in our cosmic neighborhood. So this is really for the first time in history that we can answer this century, maybe millennia old question of, are we alone in the universe? So we are the first generation that could answer this question. And obviously I'm pushing that we actually will be this generation. I don't want to wait and just have my grandkids answer this question. But we are also the generation in history who has to take very good care of this one planet that we have, which is, as far as we know today, the only one in the whole universe that has life. Thank you.
Thank you, sir, for such an insightful lecture. Ever since early humans first looked skyward and imagined the stars stars as distant campfires, humanity has wondered if we are alone in the universe. And in the 21st century, astrobiology harnesses the required technological and scientific capability to seriously address this ancient and fundamental question. Thank you for educating us for some of the intricacies and missions on the subject. And I was particularly amazed by the transit of the Mercury around the Sun. And indeed, hunting for exoplanets requires a lot of patience and precision. So now, sir, we will take up some questions which we have which people have posted in the comment section. I'll just get to our very first question. So I would like to ask this question. The technology and instruments deployed in any space-based telescope or ISS, for the matter of fact, are at least a decade old from the day the instrument is launched. How do we ensure that the instrument is compatible with the ever-changing technology on Earth?
Yeah, great question. So this is actually one of the reasons why something like Sophia is such a great idea, right? So this is what I meant by Sophia is a space telescope that comes home every morning. So as the question states rightly, right, if now that we launched James Webb Space Telescope, the instruments were built 5-10 years ago. So every space telescope, just by by the definition of the problem, is always like old technology. And unless you have an update mission, like some of you might have seen the videos of people putting new instruments on the Hubble Space Telescope, which might not be possible for James Webb, you usually really fly old technology. So this is why something like Sophia is a nice compromise, right? You can take it down in the morning, put your latest, newest, coolest camera, the fanciest infrared detector on the plane, and fly it the next day, and don't have to wait 10 years to build a satellite telescope to do it. And then if you design a telescope, like we, for example, do this live mission that you can see in my background, you really have to anticipate a lot, right? So we want to build this thing. As I mentioned, I want to see live detected before I retire. This is really one of my career goals. So we have to anticipate a lot. Where's the field of photonics going? Where's the field of formation flying going? The technology is not there yet, but we have to anticipate where the technology will stand in 10 years, in 5 years, in 15 years. So this is exactly the kind of thought process that we have to go through if we design missions like this. Yeah.
Okay, thank you so much, sir. Thank you.
So the next question is from Karan Verma. He's asking, scientists are trying to detect alien life by studying the atmospheres of distant exoplanets. How would the Earth's atmosphere be if there were no life here? In
Mhm.
other words, what changes have life forms added to the atmosphere of the planet,
Mhm.
of Earth?
Yeah, also nice question. Actually, one that one of my colleagues is working on. So Eleonora Alley, she's a postdoc in my group or in our group. She studied that. She looked at the spectrum of Earth over time. So she looked at prebiotic Earth, really in the beginning, before life emerged, and then also life on Earth before the great oxygenation event, as we call it. So you might know that Earth not always had an atmosphere full of oxygen because first of all, photosynthetic organisms had to evolve, and then they really changed the atmosphere, almost a little bit like we are changing the composition of our atmosphere right now by putting all the CO2 in it. So, and she actually looked at how a telescope like life would be able to distinguish it. And one thing, for example, that she could show is that for this prebiotic Earth, we would see the spectrum and we wouldn't be able to detect methane and oxygen because there was no methane and oxygen in the atmosphere at that point of Earth. And then, if you look at the before the great oxygenation event, you see methane maybe from other photosynthetic organisms, and then after the great oxygenation and in modern Earth, you see both fingerprints of methane and oxygen. Yeah. So this is actually something, and usually how we approach this problem, of course, we would say, okay, if we put Earth and the Sun at 10 light years, 20 light year distance, would our telescope be able to distinguish these cases? Again, exactly the question how we approach the problem here. So really smart audience, I see.
Thank you so much, sir.
Okay. So our next question is from Aman Jha. He writes, most scientists agree if aliens showed up in our atmosphere, it would almost certainly be bad news for us. Even Stephen Hawking once said, we only have to look at ourselves to see how intelligent life must develop into something we wouldn't want to meet. Most likely, they'd be searching either for resources or a place to colonize. What do you think about this?
I mean, this is all speculation, right? So, but I think it's a really nice way also to reflect on ourselves, and this is where this whole sociology comes into play, right? So it makes us reflect on ourselves, right? So are we good for our planet, or are we, we are at the top of the food chain and we are not really nice to all the other organisms? So if someone even farther up in the food chain comes here, would they be nice to us? I mean, it's a question to speculate about. Some people say, yeah, if something is so advanced that it can fly between stars, it might also be, beyond wars and beyond exploiting, lower life forms. But this is all speculation. But what makes it so interesting is that not to find. I mean, it's also obviously interesting if we would find them. But what I think is already super interesting is the way we can use these thoughts to reflect on ourselves, right? So to think about, are we treating animals right? Would we want to be treated by a higher life form as we treat our lower life forms, for example, right? Or, are we treating our planet how aliens would treat their planet? So I think even from that perspective, if we find aliens or not, I think just going through this thought process, we learn a lot about ourselves as a civilization, right?
Yes, correct.
Right.
Thank you.
So the next question is from Priyanka Sharma. She's asking, if you were to bet on one place in our solar system beyond Earth where life could exist, which one will you choose?
Good one, good one. So I mean, Europa is a good one. There's a lot of water and actually a couple of other moons. I think even Titan has an underwater ocean under or a water ocean under the methane ocean, as far as I understand. So Mars could be, at least it might have had ancient life, and there might still be some microbes, hiding somewhere, below a rock at the poles or something like that. So maybe even Venus, some very exotic life forms in the atmosphere of Venus. So I think there are a couple of contenders. So if I had to bet, I would probably do a split bet and put like 50% on Europa and then 25 on Mars on Venus or something like that.
So if we say just one place, it would be Europa.
I think for the likelihood that life is there, it's all speculation, right? It probably is Europa because of the water mostly. But then the other question is also if it's about finding life there, it's also much easier to find life on Mars and Venus because they are closer and they are bigger planets than Europa, right? It takes a spacecraft, a year to go to Mars, but 10 years to go to Europa. So it's always a trade-off. Life might be less likely on Mars, but it's much more easy to find, right? And if you trade these off to each other, it might actually be more likely to find life on Mars, even if it's less likely to be there because it's just easier to observe.
Thank you so
Okay.
much, sir. That was
Thank you so
interesting.
Correct. So our next question is from Subharti. She says, you talked about plotting the brightness from distant stars to track down planets in orbit near it. But how do we exactly understand the distance of the planet from the star?
So this is, as I mentioned, we have this dips in brightness, right? So every time the planet goes between us and the star, the light goes down. And then if you observe that a couple of times, you will realize, okay, it happens every 14 days or it happens every 50 days. So then we know the planetary period is 50 days. And then there's really, let's say basic astronomy, Kepler's law, some of the oldest, laws in astrophysics, very basic gravitational law can directly describe the relationship between orbital period and distance. So if a planet has, a 1 year orbit, it has exactly the distance as Earth has from the sun, for example, right? And this is everywhere. If we find another planet who has a 1 year orbit around a solar-like star, we know it's the same distance as Earth, for example. So the orbital period is directly connected to the distance. So if once I know the orbital period, I know also the distance. Yeah.
Okay, sir. So the next question I wanted to ask. So the question is, when we are looking for signs of extraterrestrial life, are we looking for signatures of carbon-based life forms alone? If not, then what other element-based life forms could exist in the universe, and what are the ways to detect them?
Yeah, so this is a question that comes up very often. And I think in general, we have like two general approaches to find life in space, right? One is you look for, life as we know it, right? So we look for oxygen and methane and follow the water and look for carbon-based, life forms. But then there's also this other approach that I kind of hinted at, is that we also in general just look for anomalies, right? Just look for atmospheres that are out of equilibrium, for, planets that shouldn't be where they are, or, elements like some of you might have heard about this phosphine that might have been found in Venus atmosphere. So just molecules that shouldn't be there under normal circumstances. So these are roughly these two approaches. On the one hand, really look for life as we know it, but also in general just look for, weirdness, just for outliers. And then when it comes to life based on other chemistry than carbon chemistry, there's some studies. I'm not a super expert on it, but what I heard or what I read is that, for example, one example would be silicon-based, to just replace the carbon atom with a silicon atom. But then first of all, it happens under really low temperatures. So this should be much lower temperatures. And then the chemistry is really slow. So you wouldn't probably evolve as complex life as you would with carbon-based chemistry. So you might have very, very basic life, but if you had something like a human but not based on carbon, it probably would take longer than the age of the universe to just move your arm, because the chemistry is so slow under these low temperatures. But again, I'm not a super expert in this. This is just this analogy that I have in mind, that this other chemistry handles under very cold temperatures, and that it really slows down things a lot. So. But, the universe is so big, there's so many things that we don't know. And definitely one question that is also part of this, the canon of astrobiology and people looking into it. Yeah.
Thank you so much, sir. So now we have a very special guest with us from the Press Trust of India, Shakur Rathur. I would request Preksha to add him here. Thank you. So welcome, Shakur.
Hi, yeah. Good evening.
Hi, Shakur.
Yeah, I would like to ask you a very non-technical question here. Since we are in a pandemic for the last 2 years, so I would like to know from you, how has the pandemic impacted the astrobiology research so far?
Oh, on very many levels, I think all of the life. So first of all, our conferences got cancelled or went online. So can you maybe mute yourself, if possible? Okay, yeah. So first of all our conferences got cancelled. So that's tough.
Shakur, I'm sorry to interrupt. Shakur, can you mute your mic? Yes.
Okay, yeah, now it's better. Yeah. So first of all, first order, our conference got cancelled or went online. So I haven't seen any of my colleagues in 2 years now. I mostly work from home. So in between, there were the months here and there where I could go to my office. For me personally, it was funny that or weird that I started a new job just in March 2 years ago. And then after 1 week, we went into lockdown. So I basically knew all my colleagues just from Zoom. And then it was kind of weird when I went back to the office that I met a couple of the folks that I just knew from Zoom, and they were like 2 heads taller than me, and I just know them up to here. And then I realized, okay, these grad students, they are a basketball team, right? So these are like the things that happen if you don't work online. And then I think more practically, so there are, for example, colleagues of mine who work with microbes in the lab who couldn't go to the lab or had to get extra permissions to go in the lab, so that their microbes that they grew for years don't just die in their petri dishes. So I think as everywhere else in public life, it had a huge impact. I'm also very sorry actually for a lot of the grad students, for example, that graduated during this time. I mean, your graduation is like one of the biggest moments in your life for many of us in our careers, and you want to celebrate it. You want to invite your family. You want to have a small reception afterwards. And many of my friends who graduated over the past 2 years just did it like we did it here in the Zoom. Right? They were alone in their room in front of a green screen talking to people on a screen. I mean, this is really, on this emotional level, something that I'm really, really sorry for. And I'm always kind of pushing that once we are through this pandemic, we should have like one big conference for all the people who graduated in the meantime, to have just a big party afterwards to make up for all these graduation ceremonies that they had to do their own in Zoom or wherever. So yeah, big impact too for everyone in science as for the rest of the society, I think.
It's mute.
Yeah, my second question is, when we talk of intelligent life, so how much is the evidence so far, of finding intelligent life? And do you think that, asteroids and moons, exomoons, are a better bet for finding, life than say a planet? Like we talked about Mars earlier, because it's more accessible than many other exoplanets.
Yeah, so two questions. The first about the likelihood of alien life. Can we move this? Oh, yeah, perfect. Yeah, so the likelihood of alien life. So this is similar to some of the other questions we already discussed. So we don't know much yet, right? So we only have this one place in the universe where we have life, where we have intelligent life, and then some people argue, yeah, if life happens so quickly on Earth, why there should be life everywhere, right? But this might be a coincidence because we wouldn't exist if life hadn't emerged early, right? So you can make this thought. Then intelligence, it took like 4 or 5 billion years on Earth to evolve, intelligence, right? So it might not even be, a genetic pressure to become more intelligent. The dinosaurs were here for hundreds of millions of years and they didn't have cell phones or telescopes in the end. So there might not even be evolutionary pressure to become more intelligent. So intelligence indeed might be super, super rare. So a colleague of mine, Dave Kipping from Columbia University, he wrote a paper about it. He also has an amazing YouTube channel, Cool Words it's called, you should check it out, where he talks about one of the topics that he wrote a paper about is that he took this number, this one number that we have is the Earth, with life very early and intelligence pretty late. And he concluded that actually there's a 60% chance that intelligence is really, really rare in the universe. So that's I think one question. So this is, I'm agnostic there. I'm just, a scientist. We don't know an answer. And from what I know from the literature, it could be both right now. So we can't even constrain it very well. So something that Dave did, like the 60% chance that it's rare, is probably the best we can answer this question right now. And then the other one that you ask, also great question about, how about looking for life on exomoons? Wouldn't that be maybe better environments? The answer is similar to what we talked about for life in our solar system. So it might actually be an easier place to, have the right conditions, the right temperature, maybe water on the surface on a moon around an exoplanet. But then it becomes even harder to observe the moon next to the exoplanet, right? We don't have to just cancel out the star, but then we also have to cancel out the planet to then see the moon, right? So life might be more common on these exomoons, but it is an order of magnitude harder for us to observe these exomoons, right? So it's again this trade-off between life might be more likely on these exomoons, but much harder to find. Or there might be lots of planets where life is underground, but doesn't interact with the atmosphere. And we can't remotely detect something that happens underground on a different planet, right? If the life doesn't interact with the atmosphere that we look at, we wouldn't even be able to find it, right? So it's always this trade-off between how likely is the Earth in this environment, but also how good can we observe this environment to really get this full chance of finding life there.
Okay, you're on mute.
Yeah, my final question is, what percentage of science fiction do you think has now become a science fact? Because earlier we used to talk about planets like Tatooine in Star Wars, but now we know a planet like a planetary system like TRAPPIST, which has planets with 2 suns. So similarly in other fields of science fiction, how much do you think of that has become a reality now?
I think it's a two-way street, to be honest. So I think a lot of myself and a lot of my colleagues are actually inspired by science fiction. So a lot of us chose astronomy because they watched Star Trek or Star Wars. So I think there's this one way, and a lot of people also, for example, start about why should we look for, they might be inspired by Tatooine to actually look for planets around binary stars, right? And then the other way around is also that we find planets that are even crazier than any science fiction authors even imagined, so that they come to us to want more information about it. I just got a mail from someone who's writing who's writing a science fiction story about so-called tidally locked planets. So planets that always show the same side to their stars. So you basically have a planet which has one permanent day side, one permanent night side. And of course, you can imagine, there might be some crazy stories you can evolve about, the people living on the day side, the people living on the night side, or whatever. But this is something that no science fiction author even came up with until we found these tidally locked planets, and then they started to think about it. So I think it's a really two-way street, inspiring science fiction, and then again, science fiction inspiring, then science inspiring science fiction back. Yeah.
Thank you so much for joining us, Shakur. And that was amazing questions and some amazing answers here.
So we
Thank
have
you.
the last question, sir. Harsh is asking, what is the possibility of finding life on rogue planets?
On rogue planets. So
Yeah,
planets without stars.
without stars. Yeah, the free floating planets.
So first of all, I mean, this is actually something that is also super new that we never really thought about. I mean, some people thought, in the process of planet forming, and if two solar systems collide, there might be planet thrown out again. And then people think, there might be, maybe even more free floating planets than actually planets around stars. Then there's of course problems with it, right? If you don't have a star, it's probably pretty cool. So you need some kind of internal heating or another heat source to keep that planet warm enough to have life. Then you might not have the right ingredients on these planets to really make life, and you need an energy source. So it might be hard to build life and contain life on these rogue planets just because they don't have a light source. But this is again just extrapolating and speculating from what we know on Earth. But then it also comes back to this question I said before. So these rogue planets are super hard to find, right? So we wouldn't even be able to find them, and even if we know where they are, it would be pretty hard for us to observe them if there's, for example, no light from a star that's reflected by them or something like that. So then again, similar to the question that Shakur just asked about the exomoons, right? There might be plenty of life on these rogue planets, but we wouldn't be able to observe them. So it might be more likely to have life there, maybe, but it's much harder for us to observe it. And this is exactly this trade-off we always have to think about. When I think about this telescope in the background, where should I point it to have the best chance to find something, right? It might not be pointing it at the planet with the best chance for life, but it might be pointing at a planet that might have a less likely chance to have life, but it's more easier to observe, right? So this is really the thought process we go through if we plan our observations. Yeah.
Okay, sir. So I think that was the last question. So, on behalf of the Secrets of the Universe and Gurukul Academy, I once again extend my very hearty gratitude to Professor Daniel Engerhausen for accepting the invitation and sharing with us his valuable thoughts. Your thoughts have enlightened our minds and have shown us a new path. I would also like to thank all of you for joining us from different parts of the world. It is your love and support that keeps us going and inspires us to continue our work. Stay tuned on our channel for many such talks on the coming Saturdays. Thank you.